Afternoon.
18?
All right, so
Yeah.
we're picking up where we left off yesterday. And we, in lab 11, yeah, 11, we had to figure out the Ka of our acid, and we can do so because we have a new derivation, which is the Henderson-Hasselbalch equation. And I want to go over that now and show you the implications of what we call this buffer region, or I call this buffer equation. Okay, so in any case, in lab 11, we had a weak acid. It was acetic acid, vinegar, as we say in West Hampton Beach. We don't say vinegar. All right, so we had vinegar, and the net ion equation is vinegar. Okay, let's say it's going to dissociate into a proton and its conjugate base. And it being a weak acid, we know it's going to make what kind of a strength of a conjugate base?
A strong conjugate?
Yeah, and that's the difference in the two titrations. It's really important that you understand the difference is that we have that conjugate base who can react with the water to produce hydroxides that didn't happen in the strong acid and strong base titration. Okay, that's the reason why the pH at the equivalence point is above 7. Okay, it's the reason why it rises up a little bit. All right, so let's talk about this for a reason. And I want to derive this for you. I know you can't wait for me to do it live in class, but I can't help but do it again and again and again. So I have this formula, and this is an equilibrium. It's a weak acid. It barely goes forward, but we like to use this designation, Ha, for the acid. That's the conjugate base with the proton. So this is the conjugate acid. And after it dissociates a proton or gives that proton to something, acids donate protons, okay, it becomes a conjugate base, one less proton. So there's a conjugate acid-base pair. And because vinegar is a weak acid, the conjugate base has some ability to grab the proton from water, okay, and reform the acid. So this barely goes forward. Now, let's talk about what a Ka is. A Ka is an equilibrium, okay? An equilibrium formula, just like your lab. By the way, lab 2 has been graded. For those that my full remote students, I will have that done today, okay? Also, I put in the RAT 3 test, okay? So hopefully you can see that the grades this quarter are fair. Any case, equilibrium constant is what? Products over reactants, or the concentration of the products over reactants. These are all aqueous, so I can have a concentration. If they're solids or liquids, I could not apply here. So products over products over reactants, coefficients become exponents, solids and liquids do not apply. They all have a coefficient of 1, that's implied. So that's my Ka formula, just like we did in our test. Now, what I'm going to do is I'm going to separate this, okay? I'm going to put the H plus over 1. And I'm going to times it by the A negative, the conjugate base, over the HA. That's equivalent, okay? And so what I'm going to do now is I notice that, wait a minute, there's an H plus hanging out there. If I negative log that, I got pH, okay? So what I'm going to do is I'm going to negative log both sides. So I negative log my Ka, which means I put a little p here, little p, okay? And that's Ka. That's what negative log means, okay? I have this expression here. I'm going to negative log both of these, okay? So this becomes negative log and negative log. The negative log of the H plus ion concentration should be the pH. That's all I did. I separated because I know there'll be pH. Now I'm going to times it by that negative log of that expression, which is conjugate base over the conjugate acid. Ha! All right? And then we're going to solve for pH. Well, we solve for pH, little p. Everyone's happy there's one period today. Little pH. Hey, I'm going to do plus negative log on this side, right? plus negative log of this. I'll write it all out. I'm invested entirely. That's going to cancel. And I'll do what? Plus log of the A negative over HA over here. And what do I get, party people? I get pH is equal to the pKa plus the log of A negative over the conjugate base Ha. That, my friends, is the Henderson-Hasselbalch equation. And it tells us something that we can use with a weak acid. We can get after and find the Ka. All right? I'm going to rewrite this nice and pretty and keep it over here because we're going to use it. Okay? So let me just write this nice and pretty. So all of that got me to this. The pH is equal to the pKa plus the log of the conjugate base over the concentration of the conjugate acid. All right. And so last night or yesterday, we realized something. If I have a half equivalence point, and let's pull up an equivalence point or a titration curve, we know the equivalence point is exactly the volume of, in this case, base, that we need to neutralize some acid. And that volume of base has particles of hydroxide, and so this volume is equivalent to some moles. Times it, convert this to liters, 0.020 liters, times it by the molarity of our known solution, we got moles of hydroxide. And of course, at this point, it equals what? Moles of H pluses, they're the equivalents, right? At this point, we've driven all of the acid in the beaker into water. We've neutralized it, right? What's half equivalence? Well, this is the volume of base that'll half titrate. Don't forget that this reaction only goes forward a little bit sitting in the beaker. But when we add a strong base to this, it's no longer equilibrium, it's a driven reaction. And we drive it, okay, into water. And of course, the conjugate base. This is now driven. And we know that as many hydroxides as I add is exactly how many HAs it'll rip the H off. The strong base will force the weak acid to act like a strong acid in the sense that all of its H's will come off as long as there's just enough of those hydroxides. For every one of these, it'll rip one of these. It's a stoichiometric driven reaction. So if I have the half equivalence point, you should recognize that I am driving half of it into what? The conjugate base. So let's pretend I'm a princess. That's kind of crazy, but let's pretend I have 1 mole of acid. At the half equivalence point, how much hydroxide must I add to half titrate it, half drive it? If I start with 1 mole of acid, how much of the base do I have to add? If I have 1.0 mole of H plus in my beaker, how much hydroxide do I have to add to half neutralize that? Would that be 0.5? All right, 0.5. Thank you for playing. So, if I have 1 mole, 1.0, and I add 0.5, the limiting reagent is this, right? Minus 0.5, minus 0.5, 0 initially, plus 0.5. Oh, so if I am half driving it forward, what's 1 minus 0.5? 0.5 remaining. What's 0.5 plus 0? 0.5. So if I half drive it forward, I'm going to have equal amounts of conjugate what? Base and conjugate acid. That's what's special. At that point, you have equal amounts of conjugate acid. And that should make sense to you. Because at this point, there's 100% what? Conjugate acid, 0% what? Conjugate base. At this point, this will go to 0, but this goes to 0 too. You have 0% conjugate what? Acid, but 100% conjugate base. So as you get closer, you're going to get more and more base till it's equal, and now more base than acid. I mean, it's important you understand that. So, party people, all right, at this position, these guys are the same. And if they're the same moles and the same volume, the molarities will be the same. Remember, brackets are molarity. If these are the same, it goes to 1. What's the log of 1? 0. So when these are the same, this goes to 0. And what do we know? pH equals the pKa. So you go drive and find that pH, and that's the pKa. To get rid of the little p, to go in reverse, the anti-log, it's 10 to the negative value. In my example here, 10 to the negative 3. 1 times 10 to the negative 3 is your Ka. Okay? So, that's really important. This is called the buffer equation. All right? There's a reason for that. Because this equation can tell me the pH along this line right here. So let me just make up a titration curve right here. We know that we're going to have pH on the y, volume of base on the x, or the volume of titrant, and we have something like this. There's your equivalence, half equivalence. You read that off, and that's going to give your pH, which is your pKa, 10 to the negative value. You get your Ka. All right. Now, let me ask you something. If I have, in my example that I have up here, okay, the Ka here is 1 times 10 to the negative 3. Why? Because the pH equals the pKa. The pH was 3. To get the pKa, the actual number, I did 10 to the negative 3. So the pH was 3. What did I do with that? I did 10 to the negative 3, and of course that gives me 1 times 10 to the negative 3 equals my Ka for an acid. Okay, that's my curve. Let's pretend that's my curve. Okay, now, what if I give you a weaker acid? What if I have a Ka of a weaker acid? Think of it this way. What if the Ka of a weaker acid? Now, if it's a weaker acid, will the Ka be larger or smaller? What is Ka? Isn't Ka the products over the concentration of the reactants, generally speaking? If it's a weaker acid, does it go forward as well? No. So if it's a weaker acid, there's going to be even more reactants and less products. This is going to be a smaller number. You should be aware of that. So let's make a smaller number. 1 times 10 to the negative 5. Acids that are weaker have smaller equilibrium constants. They don't go as what? There's more reactants favored, smaller number. How would this curve look? Well, wait a minute. If its Ka is 1 times 10 to the negative 5, its pKa is what? It's the negative log of this number. Take the exponent times by negative 1. What's the pKa? 5. So if this is 3, make that 5. What's this look like? And what's the pH here? 5. What's happening to the asymptote as my Ka gets smaller? If I have a Ka of 1 times 10 to the negative 7, what's my pKa? What's happening to my lines? They're going up, aren't they? What's happening to your asymptote? Getting smaller. What's also, notice my pH here for the black line is here. That's my equivalence point. What's my equivalence point for the second one? Isn't it higher? What's the equivalence point for the third one? Even higher. Your equivalence point is getting more basic. Why? At the equivalence pH. Why am I getting more basic as my acid gets weaker? weaker acid, what conjugate base? As this gets a weaker acid, this becomes a stronger conjugate base. The reason why acids are not good at dissociating is because the conjugate base is really good at what? Reforming that acid. So weaker conjugate base, weaker acid, or conjugate acid, stronger conjugate base. So as the Kas get smaller, the base strength gets stronger. It's the reason why it works. And therefore, at the what? Equivalence pH, when you've driven the reaction completely to conjugate base, you've driven it forward to 100% conjugate base, that conjugate base is going to rip H's off water and make what? A lot more hydroxides. So as the acid gets weaker, this asymptote gets leveled out. Notice the limit is the strength of the base in this case. All right? That's important connections. All right? Now, there's more to it, and I want to give you some real-life connections with this. All right? Because, okay, it's chemistry. I don't really get it so much. Hey, blood levels. We talk about how important pH is in living systems. We know that the span of pHs are very, very small. The range of pH that's acceptable for life is really small. Your blood maintains a pH, we say buffered, at a pH between 7.35 and 7.45. We have to keep it there. If it goes below 7.35, you're not feeling well. If it's above 7.45, you're also not feeling well, okay? This is acidosis, which means it's more acid than normal. Alkalosis means you have more basicity than normal. Now, normal pH of blood is a little bit basic, above 7. Look at this, a little bit below 7, and I don't know if I want to be in those positions. So your blood can't have huge swings of pH. So we have to resist that. If we didn't have something in our blood that resisted our pH from swinging so low and so high, we wouldn't be here today. And what does that is a buffer. A buffer, my friends, is an acid and its conjugate base. And there's a reason why it's a buffer. Okay, in your lab 11, what was our acid? It was H, let's do this. It was what? It was HC2H3O2. That's vinegar. Its conjugate base was C2H3O2, negative. This was the conjugate acid. Here's the conjugate base. At this point here of our titration that we did yesterday, that's a max buffering position. Why is it max buffering? Well, why is it a buffer position? I said yesterday that this position here, you get rid of all of this position here, below the equivalence, right after initial pH, this position here is a buffer region. Why? Because as I drive the reaction forward a little bit, I make conjugate base. And I have some acid that's remaining. So in these positions here, along this line, and below the equivalence, right after the initial pH, I've got two of these chemicals that are existing at the same time. And they do not neutralize each other. Why? Well, if this is a weak acid, this is a what? Strong conjugate base. Because of their inverse abilities, they don't react with each other. That means in this beaker, in the beaker that I'm titrating the acid with, the weak acid, up in this area, not at equivalence, below equivalence, right after initial pH, I've got both of these chemicals existing. Why is it a buffer solution? Well, it's a buffer solution because if I have acid and base, both in the same beaker, and they must be conjugate acid-base pairs, hey, if I add some base to this, the acid will neutralize it. If I add some acid to this, the base will neutralize it. That's what a buffer is. A buffer is a conjugate acid-base pair that can prevent pH swings. Your body has a buffer. By the way, look at your curves. Okay, look at the lab's curve from yesterday. Okay? If you look at the curve, and I know that's not a good example. If you look at the curve, let's go to the video. Not the review. Here it is. Weak acid, strong base. If I go to the curve, maybe it'll play. Cool, maybe. And we'll go over here. And I'll make it big. Why isn't this just rising up? Why is it leveling out? It's buffered. We're adding base to an acid, but it's just not rising up. It's resisting it. It's buffered there. There's a buffer region, okay? All right, now, so let's go back to why this is pretty important. Maybe, if I can get off of this. Okay, let's get off of this. Now, let's talk about pH levels. What actually is the conjugate acid-base pair in our blood that prevents our pH from swinging? It's very low pH that could kill us, or very high. By the way, the pH of lemon juice is about 3. If our blood got to become like lemon juice, we're long gone. It's 1,000 times more acidic than our blood can get to. We've got to prevent that. And because there's so many there's so many acid-base chemicals that have acid-base properties, we have to keep our blood pH, okay, at a very narrow range. So here's what we use, okay? And I'll keep that range right there. Hey, here's what we have. In our bloodstream, we have carbonic acid, there's a conjugate acid, there's the conjugate base. And this exists in our bloodstream, okay? What does the conjugate acid do? Well, it can neutralize bases. Why? Because it can donate that proton to the base to neutralize it. Why are bases bad? Why can't the blood get basic? Can't the base break down proteins? Can't the base push electrons on? Did we talk about that? So bases can break down and denature proteins. And we should learn in biology, you mess with our proteins, you mess with our ability to many different things. Okay, or our soldiers of our DNA, our expression, are our proteins. And of course, so is our immune system. All right? Hey, what about if you have too much acid? Well, won't the conjugate base neutralize it? And we know that acids can pull electrons and denature proteins as well. So by having both pairs there creates the buffer. The buffer is a conjugate acid-base pair. Interesting enough, this is how it works. As a product of respiration, cellular respiration, we take and make ATP by taking in glucose, we produce CO2 in water. CO2 diffuses through the cell membrane. Remember, CO2 is nonpolar, cell membrane is nonpolar. So it goes through by Le Chatelier's principle, or by high concentration, let's say diffusion, it goes from the high concentration of the cell and diffuses into the bloodstream, into the plasma, the liquid part of the blood. And when it mixes with this, we learn that CO2 is a Lewis acid. It produces this guy who gives off a proton. So, just by using glucose, cells naturally making ATP from glucose, we build up protons. Our blood starts getting acidic. And it drops our pH. We don't die, do we? No, we buffer that a little bit, but our pH does drop. Now, we have a proprioceptor in our bloodstream, or I would say in our aorta, the biggest blood vessel we have, and it picks up pH, or H+ ion concentration. If this gets too high or a low pH, it signals our autonomic nervous system to start breathing. And what do we have in our lungs? Alveoli with a high surface area that's wet and moist. When we breathe, we push out the CO2 out of our lungs. Hey, Le Chatelier's principle. If I lower the CO2 by letting it expel out, remember, high amount of H pluses lowers our pH. We produce CO2 in our plasma. That triggers us to breathe, or forced to breathe, by our autonomic nervous system. If you ever tried to hold your breath a long time, the best way to do it is hyperventilate. By doing that, I'm pushing out extra CO2, I'm raising my pH, so that takes a longer time to lower to be triggered. But anyway, as the pH drops, because this gets too high, as CO2 hits water, okay, it triggers our autonomic nervous system to start breathing. By breathing, we push out the CO2 out of our alveoli, and by Le Chatelier's principle, so cool, what do? By lowering the CO2, we shift this equilibrium this way, and we're going to use up the H plus, and our pH rises. But that's our buffer. Kind of cool how it works. And this is not just something I'm making up or you have to learn for AP Chem. We're surrounded by industrial processes that do organic type of chemistry, and most of them do, when you think about it, need buffers to keep the what? The range at a place that allows for the reaction to occur appropriately. Okay. Any case. Now, what is the Pka of H2co3? What does that mean? What is the Pka? Start thinking in terms of graphs. Okay? What is the Pka? Let's draw our Henderson Hasselbalch again. Start thinking in terms of titration graphs. So the Henderson Hasselbalch is pH equals the Pka plus the log of the conjugate base over the conjugate acid. By the way, this is given to you in your reference statement. They're saying that Pka of this conjugate acid is 6.1. What does that mean? Well, if you think in terms of your graph, if I was to do what? Titrate it, that means that this point right here is what? What is the pH right there? If the Pk is 6.1, if this is equivalence, and this is half equivalence, what is that point right there? 6.1. The Pka equals the pH at the half equivalence point. So that is what? 6.1. So what does that mean? Well, the max buffering position for these two is 6.1. Why is it max buffering position? Because we have the greatest amount of A, or a conjugate base, and conjugate acid. Why is that max buffering? Having equal amounts of conjugate acid and conjugate base means you're able to buffer in both directions. The greatest. But wait a minute. The blood needs to be buffered where? Is the blood buffered at 6.1? If the blood buffers at 6.1, we'd be dead. It needs to use this and buffer it at a higher pH. Whoa. We need to buffer it like right around here, 7.4-ish, which means who needs to be in greater quantity? Look at this formula. pH equals the Pka. The Pka is what? 6.1. Who's the conjugate base? HCO3 negative, correct? So to be able to buffer right there, do I have to have more conjugate acid or more conjugate base? Think with me. 6.1 plus. If I have more conjugate base than conjugate acid, and you should see that's true, right? If this is bigger than 1, the log stays positive, and you're adding to this. If I have more conjugate acid, that'd be in this region, this number is less than 1, which means the log of number less than 1 becomes negative, and you're subtracting from 6.1. You need to realize to be in this position here, above max buffering, you've got to have more what? Conjugate what? Base. And you should know that. At this point we have what? 0% conjugate base. It hasn't been driven forward. At this point we have 50% conjugate base and 50% conjugate acid. Here we have what? 100% conjugate base. So as you go forward, the amount of conjugate base increases as we drive this formula forward by adding hydroxides. So being above the half equivalence point means that you have more conjugate base than conjugate acid. That should make sense to you. So we know in physiology, when they look at the blood, they always see that the blood, generally speaking, in a healthy individual, has 20 times the conjugate base than of the conjugate acid. Well, they come up with that, but we can solve for that, party people. Hey, Henderson-Hasselbalch, you have this. We know the pKa of the hydrogen carbonate, 6.1. And if we didn't know the pKa, we just grab the Ka and do negative log. We want a buffer at 7.4. Here's the log of these two. Conjugate what? Base over conjugate acid. Okay, I want to find that ratio. So I subtract 6.1 from 7.4, just doing some algebra. I get 1.3. I'm left with this expression. To get rid of the log, I do 10 to the x to both sides. 10 to this just makes it this. And this becomes 10 to the x here. It's a logarithmic function. Hey, 10 to the 1.3 is 19.9. What does that mean? 19.9 equals this, so it's a 20 to 1 ratio. You need 20 times the conjugate base. And that's what they say in the books all the time, but the Henderson-Hasselbalch proves that. Okay? And what would this look like on a titration curve? Okay? Just like this. We're below the what? We're below the equivalence point, but above the half equivalence. And that should make sense to you. All right? Why should that make sense? Why should that make sense? Again, this is what? 50% HA, 50% what? A negative. And as I move here, I've got a greater amount of conjugate base until I have 100% conjugate base at this position. And I have 100% A negative. That means we've reached the completion. You've driven that away. There's 0% acid. So it should make sense. The amount of conjugate base is increasing. Here it's equal. Here it's above. If it's above, this part's bigger. You're adding to that value. Okay? So that's what I wanted to talk about today. What's a buffer? Conjugate acid-base pair. It's an acid and base that can coexist without neutralizing itself. Why? Because they have reciprocal abilities. Good, strong acid, weak conjugate base. They can't react with each other. All right? And this is what we call the buffer region. So when we talk about the Henderson-Hasselbalch, we can solve for what the pH is on any part of this curve as long as I know the Ka or pKa and how much of the conjugate acid-base pair. But put this in your memory banks. When these are equal, has to be that point, these equal, pH equals a pKa. All right. Now, one little point from your homework that people got wrong. They didn't know the difference between an endpoint and a equivalence point. That's our lab. We have lab tomorrow? No. You guys have lab Thursday. So we'll come in, we'll do that. But here's our strong acid, strong base. Hey, the equivalence point is 7. Oh, weak acid, strong base. Equivalent point is not 7. What's the difference? What's the difference? What is the difference here? You have to know. Well, in the case of lab 11, what was the conjugate base that we had? Here's the conjugate base that we had. I want to put it up here. We took acetic acid, HC2H3O2. We drove it forward with hydroxides. We ripped the H off. We made water, but we were left with what? C2H3O2 negative. That's the star of the show. And when we matched all the hydroxides with this, that's the equivalence point. That means we have 0% of these guys left, but 100% conjugate base. That conjugate base, C2H3O2 negative, sits in water. Has an ability to be a base. It rips H away, so reforms the acid, HC2H3O2, and makes hydroxides. Your equivalence point is going to be above 7 because, right here for a weaker acid because you got a stronger conjugate base. Last point, and we're going to get to the start of our homework. Okay, last point is what's an appropriate endpoint? People get confused the difference between an endpoint and an equivalence point. It was part of your homework. The equivalence point is always where the hydroxides equal the acid equals the base. That's where we match protons with hydroxides always. That never changes. The end point is where the titration stops if you don't use a pH probe. If you're doing this without, okay, plotting a pH, you don't see this asymptote. You're going to stop the titration when the color changes. So to pick an appropriate indicator, we want to be as close to the equivalent point as possible, or just beyond the asymptote. If I was using methyl red for this strong acid, strong base titration, guess what? When the red just starts turning to be orange, I'm right here. I'm not at the equivalence point, I'm below it. But how do we use the equivalence point? Don't we go get a volume? Don't we use the volume of base added? But isn't that a straight line, and a tangent line? So what's the difference between here and here? None. Now in truth, they're not always perfect. But the difference between where you stop based upon the indicator, the end point, is insignificant if you were to stop right here. You probably can't even measure that. As long as we're close to the end point, which means you're on the asymptote, on that tangent line, okay, the volume will be similar. Okay? Now if you had a pH change that changed here, that would not be appropriate. You're not close. You're going to have a volume that's far off. But what do we know? Okay? As the Kas start getting smaller, this starts to flatten out, doesn't it? And therefore your asymptote. So methyl red was appropriate because you have this big asymptote in strong acid, strong base, but it's not appropriate here. It's not on the asymptote. Which means you're going to get a volume that's far away from the actual volume on the asymptote. So the end point, if you were to do this, and we'll do this in our lab Thursday, you're going to stop the titration at the color change. When the color change persists for 30 seconds. And that's the end point. Is it the equivalence point? No! It approximates the equivalence point. All right. So, your work of home is a worksheet that we did, started at home, and you're just going to finish it. Just one worksheet. You should have 1 through 3 done. I was going to do some more here, but I got long-winded as a tall teacher. All right.